Okay, let's go ahead and jump into some examples. So I'm going to start with formulas. That's probably the messiest one, but we'll go ahead and start there because that's what you've just been doing. So here I've defined functions m and p. And actually, I even want to say something before I jump into any of the rest of this. I'm going to go ahead and say right now that m and p both have a domain restriction. M is valid for all real numbers except x equals 5, and p is valid for all real numbers except x equals -3. So at some point, we'll want to refer back to that. Okay, so this first chunk, A, B, C, D, I just want to look at, can I get the value of this from using the formulas I've got? And then later on, down on F, I want to go ahead and build formulas for the combinations of the two functions. So what I want to say is that if I want m plus p of 2, that's the same thing as finding m of 2 plus p of 2. So finding m of 2, finding p of 2, adding them together. So again, when I write it as m plus p of 2, I'm emphasizing that m plus p is this new function that you would get a formula for by adding functions m and functions p. So m of 2 is 3 over 2 minus 5. So that's 3 over -3, which is -1. And p of 2 is 2 minus 2 over 2 plus 3. So 2 minus 2 is 0, 2 plus 3 is 5, 0 over 5 is 0, which means the value is -1. Similarly, p minus m of -2, you could get that by finding p of -2, finding m of -2, and subtracting. So p of -2 is going to be -4 on top and 1 on the bottom. -4 over 1 is just -4. And then we're subtracting m of -2. M of -2 is 3 over -7. So it's going to be what was I saying? 3 over 7. Yeah, -3/7. So that's going to become a plus. And I'm going to go ahead and get a common denominator. So I want a common denominator of 7. I'm going to multiply 4 by 7, -28/7 plus 3/7 is -25/7. Okay, so I want to do a little side example. I know I have this in later problems, but while we're looking at the formula, I want to point out that this starts to make it feel like you can distribute when you're working with functions, and that's not really what happens. So it's not that I'm distributing 2 through the parentheses, and I want you to try and keep yourself really clear on that. It's that the definition of the function m plus p is function m added to function p. That's how we get that function. So just to point out when this could cause trouble, I could take m of, what do I want to do? 2 minus m of -1, and that would give me, let me make a little side thing. Okay, m of 2 is, we already did that one, didn't we? 3 over 2 minus 5, 3 over -3, which is -1. Yep, we did that in the first one. There it is. And then m of -1 is 3 over -6, which is -1/2. So when we make this addition, we're doing -1 plus 1/2, which is -1/2. This should not be confused with m of 2 minus 1. You can't distribute the m through the parentheses. M of 2 minus 1 is simply m of 1. Just work in the parentheses first. And m of 1 is 3 over -4, or -3/4. So do not generalize. This is a really big problem, and it's something you want to think about. Students like to generalize, and I get it, because these generalizations are what we work on in algebra. We use them all the time, but they want to take them and generalize even more than they should. So distribution specifically works when you're multiplying and one of your factors or both of your factors are sums. You can distribute multiplication through addition. You cannot distribute functions. That's not what I'm doing in parts A and B here. Okay, I'm going to erase all this mess I just made because this is looking like a disaster to me. So do not distribute functions. Okay, so m times p of 0 is the same as m of 0 times p of 0. M of 0 is negative 3/5. P of 0 is negative 2/3. And when we multiply, those signs are going to go away. The 3's actually cancel, and I get 2/5 out of that. And then m over p of negative 4 is the same as m of negative 4 over p of negative 4. M of negative 4 is 3 over negative 9, or negative 1/3. And p of negative 4 is negative 6 over negative 1, which is positive 6. That's kind of nice at least. I'm going to write that as 6 over 1 because I have a fraction division problem, which means I'm going to need to multiply by the reciprocal. So it's going to be negative 1/3 times 6 over 1, which becomes negative 2. Okay, so if you're asked just to plug numbers into these things, you can just go through the two functions separately. If that was all I was going to do, that's exactly how I would do it. I'm going to switch colors so you can see through all my mess. I also have here that we should calculate the average rate of change of m minus p from x equals negative 1 to x equals 2. So remember, the way that looks is you take your function, which in this case is m minus p. Ooh, that's really light. I'm going to make that a little darker. I don't know if that's annoying for you to look at, but what do I have that's dark? Oh, I'm on kind of a dark one. I don't know. We'll try this and see if it looks any different. Okay, and no. Hold on, let me try one more thing, and then I'll quit being distracted. Is it too opaque? Let's take that down. Okay, so we want to take our function. Oh, that's way worse. Okay, I lied, not one more thing. Opaque. I want it to be opaque. I don't want it to be translucent. Okay. We want to take our function, that's much better, m minus p, and we want to evaluate it too. And then we want to take our function and evaluate at negative 1, and we want to divide by 2 minus negative 1. So I'm going to do this as some side work. So over here I'm going to say if I want m minus p of 2, in fact, did I do that earlier? Nope, I did m plus p of 2. So I can say that's m of 2 minus p of 2. I did do that up above. M of 2 is negative 1 and p of 2 is 0. So this is negative 1 minus 0, which is negative 1. Okay, so on the top of the fraction I have a negative 1. I want to do the same thing, but with negative 1 being my input. So now I want m minus p of negative 1. So that's going to be an m of negative 1 minus p of negative 1. M of negative 1 is 3 over negative 6. Why do I feel like I did that earlier? Maybe I didn't. I distracted myself. Okay, so 3 over negative 6 is negative 1/2. And then p of negative 1 is negative 3 over 2. Okay, and if we take negative 1/2 and we add 3/2, what we get is 1. So we're going to have negative 1 minus 1 over 2 plus 1, which is negative 2/3. So that's our average rate of change for this function. So I guess what I want to emphasize there is just that the notation looks pretty messy, and that's what we're practicing, is being okay with that and being able to sort it out. So when I write this as m minus p of 2 over m minus p of negative 1 divided by 2 minus negative 1, that looks pretty messy. But if you can kind of keep track of what this means, we want to find the output of the function at the two different x values, and then just calculate a slope. So just try always to see that simpler problem in the mess. That's always what we're trying to do. Okay, so let's check out actually finding the formula for some of these things. So p minus m of x, this is the same thing, let me move up just a little, as finding p of x minus m of x, right? That's how we get the function. And p of x is x minus 2 over x plus 3, and m of x is 3 over x minus 5. And really that's just fine as a formula. To simplify, if you need the algebra practice, you could get a common denominator. If I was going to work with this more, I might want that. But I would say in general, I would be fine with this as your answer. The new function is this, has this subtraction in it, and that is okay. We're also supposed to state the domain of the function. So often this is really easy because you can just look at what you've got. But if we refer back to up above, we know that we should never plug 5 into m, and we should never plug a negative 3 into p, which means for the function p minus m, we can't plug in either of those. It's not good enough if I can plug negative 3 into the second fraction, but not the first fraction down here. I have to be able to plug it into both. So the domain here is x can't be 5, and the and is important. I won't pick on you guys too much this quarter, but it is actually an and not an or. I want both of those things to be checked. Okay, so again, generally when you're combining the two functions, it just kind of becomes a combination of their domain restrictions. When you divide, you have to be a little bit more careful. Okay, so now we want m times p of x. So remember, this is m right here, and this is p right here, because I'm going to scroll a little bit. So m times p of x is the same as m of x times p of x, which is the same as 3 over x minus 5 times x minus 2 over x plus 3. Here, multiplication's awfully easy. I think I would definitely take the next step and say that's the same as 3x minus 6 over, oh, in fact, before I do that, I'd check and see if I could cancel, but I can't. X minus 5, x plus 3. I wouldn't probably bother multiplying the denominator out, although it's not wrong at all to do that. And once again here, if we're combining functions m and p, we better not be plugging in something that can't work for m or can't work for p. So the domain here, and you can see it in your final equation, it's not hidden, you could look there as well, is we can't plug in a 5, and we can't plug in a negative 3. So nothing new on the domain there. Okay, so just one more like this. We want to create m over p of x, which is the same thing as taking m of x and dividing by p of x. So function m, again I'm looking right up here to remind myself, was 3 over x minus 5, and function p was x minus 2 over x plus 3. Okay, I'm going to move up a little now. This one, the domain might get a little bit more interesting on, so I'm going to flip and multiply. So I have a 3 over x minus 5 times x plus 3 over x minus 2. And then I can do like I did before, and I can combine that into a single thing. So 3x plus 9 over x minus 5, x minus 2. And this one actually gets really interesting because if you just look at your final answer, I would say the domain is x cannot equal 5 and x cannot equal 2. And if you said that, you wouldn't be wrong so far, but you also wouldn't be done. So remember, even though I can't see this in my answer, the definition of m over p is you take m of x and you divide by p of x, and this creates a new function. M of x had a domain restriction. The domain restriction for m of x was that x cannot equal negative 3. Negative 3. And you can see it in that second step. Oh, sorry, I drew an arrow to the wrong thing. I hold my statement. I believe you can see it, but probably in the denominator and not the numerator. When we did the flip and multiply, that wasn't a bad step, but it did hide what was an obvious domain problem from us. So just because the algebra simplification made it not obvious that negative 3 was a problem, doesn't mean negative 3 isn't a problem. You can't plug negative 3 into m of x, which means you can't plug negative 3 into m over p. So it's actually not the what makes p 0 that gets us in trouble. We can see. What am I saying here? Oh, okay, hold on. Let me go back again. This is why I'm confusing myself. It's the p of x that has x not equal to negative 3. That's why it's not lining up. Okay, so m of x is fine. I can see m of x restriction. P of x can't be 0, so right here we can see that p of x is 0 and x is 2. Got that. So m of x is fine. P not equal 0 is fine. But the domain restriction of p, x can't equal negative 3, has been missed so far. So we need to add that one on the list. So basically, and this will come back with composition, you don't have a ton of practice with this, but I just want to plant the seeds for later. When you are combining two functions, the new domain is going to be a combination of the old domains. There are more than one way, in fact, of combining functions where it gets a little bit more subtle than that. But for now, the one we know is that when you divide two functions, you want to make sure you have all the restrictions for the top function, all the restrictions from the bottom function, and also you want to make sure that the bottom function is not equal to 0. So x minus 2 over x plus 3 not equal to 0. You would multiply both sides by x plus 3. And then you would add 2, and you would say x can't be 2. So again, in this case, it turned out that I could see that one in my final answer. So you just have to really watch out. Watch the top function, the bottom function for domain restrictions, and also watch for the bottom function to be 0. If you check all three of those things, you're going to be in good shape. Okay, thanks for watching. Sorry for my M and P confusion.